All right, so welcome, I guess. I'm Norbert, and that's it as far as an intro goes. I'm actually interested in you. Who here, show of hands, who here considers themselves a functional programmer? Yeah, we've got like the 5% ratio, perfect. But who here has heard about functional programming? You've heard about it, you've read some blog posts, someone bothered you about it, but for some reason, it's obviously not for you, right? This is my ideal audience. Everyone has heard about functional programming and nobody does it. Why? That is the real question I want to ask today. I think it has something to do with the name. Like, what does it mean to do functional programming? It obviously, it's not functional as in it's working, because that would be ridiculous. If that's what it meant to do functional programming, you should all be fired for not doing it, right? If this meant that you would build systems that work. But it turns out that functional programmers, we make the same logical mistakes everyone else does, and we oftentimes build systems that make no sense, or they're the wrong systems to build. So this does not help you build better systems in that sense. It comes from the definition, right? The definition, basically paraphrases, characterized by the use of mathematical functions and the avoidance of side effects. Or another way that you would phrase it would be something along the lines of, uses only pure functions without any side effects. And this definition is useless. It's actually worse than useless. It's terrible because it's obtuse in the sense that it doesn't make any sense to someone unless they already know what it means. If you don't know what these words mean, they mean nothing to you. So it doesn't help you explain anything to you. And if you already know what these things mean, then that doesn't help you in any way, right? The way I like to look at it is this is exactly the same problem, right? If you explain a monad as a monoid in the category of endofunctors, this is totally true, 100%. But either you already know this, or it doesn't help you at all. Similarly, the way I would think about it is like if you imagine trying to teach someone to drive, and you would explain it like this, right? There's an optimal braking, turn, and apex and exit point, and that is what it means to take the ideal racing line through a curve, which is true and useless, because either you know it or you don't. But these last two definitions, they're obtuse, but they're accurate. So they're only half bad. This is obtuse and invalid, because what does it mean to program without side effects? What are side effects? Side effects are the things like sending emails, reading files, making web requests, applying the brakes in a car, right? These are the observable things that our software does. So it's no wonder if someone hears about functional programming, Googles the Wikipedia page, reads that it's all about avoiding to do these things, nobody's interested. Because what is the bloody point? I mean, it might be interesting from like a puzzle-solving perspective, right? But there's no point to the application if it doesn't do any of the things that we want programs to do. So that's the problem with the definition of functional programming, as you often see it stated. Because not only is it not helpful, it's actually a lie. Because it turns out there are lots of functional programmers out there, and they are building systems that do all these things. And in fact, if there is going to be some piece of software in my car that directly is responsible for the correlation between me pressing the brake pedal and my car slowing down, I really do hope it's written in some kind of functional or data flow declarative method, which is easier to verify that it actually knows about all the different edge cases and conditions it could be in, right? So there's a problem. There's a real disconnect between what reality is and what we think reality is. And the question is why and where does this disconnect come from? And the analogy I've come up with is that we need to travel back in time. Really, really far. All the way to Aristotle. And Aristotle, he was a really smart guy. And him and all the Greek mathematicians, they come up with a lot of laws about geometry and trigonometry and the laws of mathematics, right? But they always dealt with the quoted pure mathematics. For them, it was actually puzzle solving. They didn't see any purpose in applying the laws they come up with to the real world, because the real world is dirty and imperfect. It's actually everything that mathematics isn't. And also, they couldn't figure out how to explain motion. Because every time you think about motion, it's about some correlation between, an interplay between the places and time. And things change over time. So it deals with everything that they did not want to deal with. It deals with the imperfections and things that we're constantly modifying. And they were thinking about timeless things like circles. Circles are always true, right? And triangles, the properties you have about triangles, they never change. And this is what they were interested in. And it turns out that it took a really long time for people to figure this out. It wasn't until the end of the 16th century where you get people like Galileo and Descartes. And Galileo, among all his other contributions, he figured out that time is a unit of measurement, right? That there is a specific momentum of time. That's where the word moment comes from, is that momentum is a specific measurement of time that's always consistent. You can actually count it. You can count it in the way the pendulum swings or the way the ball rolls down an inclined ramp. And he figured this out, right? And along with Galileo, you have Descartes, and among all his other contributions, he figured out what is now known as the Cartesian coordinate system. And that actually had two implications. The first is that it was because of the coordinate system, Descartes was able to figure out that geometry and algebra are the same thing. They're two sides of the same coin. Until Descartes, geometry and algebra were different fields of study. There was no relationship between them. But he managed to figure out that they are actually the same thing. You can convert a geometry problem into an algebraic problem and vice versa. And the other thing he figured out is that once you have a Cartesian coordinate system, you can plot time on the x-axis. And then you can plot functions of, like y over x or a function over time. And it was these tools that directly are linked to Newton and Leibniz coming along and figuring out what is now modern calculus and modern physics, right? And just like on yesterday's keynote presentation, which was talking about if you don't have the right tools, you don't have the right mirrors to look at nature, things aren't obvious. And these things that Galileo and Descartes figured out, which was time, was what led to Newton and Leibniz figuring out calculus, which is what led to eventually what is now modern physics, right? So there's this moment in history when people need to identify something. And once you identify it, you can name it. And once you name it, you can start talking about the properties and characteristics of the thing. And it wasn't until the age of reason that we had time. And only after we had time do we have physics and all the implications that went along with that. And that essentially is what functional programming is about. It's about identifying side effects. It's about saying that side effects aren't side effects. They're effects. And it's important that we name them, we identify them, and then we can talk about the laws of the side effects. How different ways we can manipulate it. See, this is why functional programmers keep talking about side effects. It's not that side effects don't exist in all the other languages. It's that all the other languages don't take them seriously. The way all the mathematicians before Descartes and Galileo lived in the, time was something that was passing, but they couldn't figure out that it was something that you can actually name and manipulate, right? So this is basically the most important thing to take out of this presentation. It's that you need to figure out ways to identify side effects. But what are these side effects? Well, it turns out we don't really know, right? We don't have a really good name for them. So one explanation is it's a modification of state outside its local environment, right? That's one way people explain a side effect. Another one is an observable effect besides returning a value which we could consider the main effect, as it were, right? But I find that the best explanation comes from the Perl docs, and it's this. Something extra that happens when you evaluate an expression. Nowadays, it can refer to almost anything, right? This is one of the many gems in the Perl docs, which is why Perl is always going to have a special place in my heart as far as programming languages are concerned. So just like Galileo and Descartes figured out there is such a thing as time, and Newton could take advantage of that to create calculus and Newton and Leibniz. Newton and Leibniz didn't figure out instantaneous velocity. It wasn't until like 100 years later after that when mathematicians figured out the mathematics of limits, because you need the mathematics of limits to actually figure out that you can talk about a point in time having a specific velocity. So similarly, I think we are in a similar situation. We identify that there's these things as side effects, and they're very important, but we haven't really figured out what the right names and characteristics for them are, right? We don't have the proper algebra. So for the rest of this talk, I'm going to ignore the word side effect because I think it means too many things, and it's not it's not a good enough definition. And I'm going to steal Eric Norman's idea. Eric Norman's writing a book nowadays. He just started. But right from the first chapter, he introduces this idea of data, computation, and actions. And I find that this idea is really appealing, so I'm just going to steal it for the rest of this talk. So what is data? Data is data. That's the best definition I can come up with at a 50-minute talk. Data is self-identifiable bits of information that are timeless. They are information at rest. They represent themselves and nothing more, right? Things like numbers, which can be floats, integers, ratios. Things like instances of time are some kind of data point. Things like Boolean and nil. Things like strings, keywords, and symbols. These are all kinds of scalars. And data is either a scalar or a collection. So these are examples of scalars, and you have examples of collections, things like vectors. So vectors have a semantic of there's an order, and there's an index that you can operate on. You can have sets. Sets are unordered, but they have some semantics of having unique elements, and all the operations that sort of flow out of the mathematics of sets. You have maps, which are a way of associating information with key values. And you have lists, which are a different way of talking about ordered elements that don't have indexes. So the amazing thing about data is that this is all you need, really. Like, it turns out that this is the amount of information you need to build really complex systems, right? Like, this is the key takeaway from Clojure developers. Because everyone that comes to Clojure thinks it's about Lisp or about running on the JVM. It's not. It's all about these data literals. And it turns out that once you have these data literals, everything else sort of falls into place. So we have data. And what can we do with this data? Well, let's say we're writing a Twitter clone, right? So some data aspects might be things like users, which we can just model as some map of key values. And similarly, we can have a collection of tweets as vectors of maps of some keys and values. And lastly, we can have some kind of feature of trending tags, which is, from a semantics perspective, is just a set of tags, right? So this is all the data we need to clone Twitter. And then what kind of things do we need to operate on this data? So that's where we get to computations. So remember, our goal is to figure out better names and definitions for the things that are the basic building blocks of our system. So the first is the data. And the thing about the data is that it's self-evaluating. You don't need any kind of execution engine to execute this piece of information and get back a result. If you do that, you just get back the same thing you were just looking at, right? So it's like a Quine from yesterday's talk in that sense. So it represents itself, so it has the wonderful characteristic that you don't need any language, you don't need any runtime to understand what things are, but it also means that you need to interpret it because data is timeless. It depends on a specific interpretation and context to understand how the data will be used. And that's where computations come in. So computations are functions. Notice that unlike data, there are functions, which means they're opaque. You don't know what they do until you run them. And the thing about computations is, the definition is that they are functions that are dependent only on their inputs. So given the same inputs, you will always get back the same output. And the other important characteristic is that computations, you can run them 0, 1, or many times, and it's all equivalent. So it doesn't matter if you run this function once or you call it many times. As long as you pass in the same input, you're always going to get back the same output, right? So this is what we call pure functions back in the good old days, right? But the other thing is that it doesn't matter if you call it one time and get back the result, or if you call it 0 times. You can always take a computation and replace it with what would have been the actual result if you had called this, and the system will work just the same, right? So it's an important characteristic that is officially known as referential transparency. You can always replace a computation with what would have been the result of the computation, and this results in a lot of, this gives you the ability to reason about systems because you can replace complex situations with what would have been the result, right? So instead of having an insane thing called, like the meaning of life, you just replace it with 42 and you move on with the rest of your program, right? So you can reason about things easier. But unlike data, you do, in fact, need to call it at least once or understand the semantics of what the function would do because it's opaque. And then we get to actions. Actions are also functions. But the difference between an action and a computation is an action is dependent not only on its arguments, but also when and how many times you call it. If you call send tweet 3 times, you're going to get 3 new tweets in your system, right? So the send tweet is actually dependent on how many times you call it. The like tweet is actually dependent only on the fact that you call it at least once. So it doesn't matter if you call something once or you call it 100 times. The only operation you can do is you can like the tweet. So that once you've liked the tweet, there's nothing more you can do with it. So this is what you would call an idempotent function. So it's idempotent in the sense that you can call it one or many times, you get back the same result, but it matters that you called it at least once. So by definition, it must be an action because it depends when you do that call. Similarly, a get tweet can be called 0, 1, or many times, but if you call it 0 times, you have no data. It depends on when you called it to get back that information. And for the sake of argument, we can assume that get tweet is always going to return the same result, right? Assuming the tweet exists. And the user tweets, on the other hand, it doesn't matter how many times you call it. It doesn't impact the system in any way. It doesn't create new things. So in theory, it's not doing anything. But in fact, it is an action because the result is dependent on when you call it, right? Depending on when you call it, the results are always going to change. So by definition, it is an action, it is not a computation. And there are very simple rules, but it turns out that once you split it up like this, you get a lot of nice properties that fall out of systems that are built this way. So the thing about, so we have data, we have computations, we have actions, and we like to build systems. The way you build systems is you compose these abstractions and build bigger things. So if you want to take some data and you want to compose it, you just take data, take more data, and smush it together. So you have a string, now you have a map, right? Now you have a map with more key values. Now you have a collection of tweets, right? And over there on the right, now you have a collection of tweets, and I've annotated every single tweet with additional like nested data structure about the user. Each of these things are self-sufficient pieces of data. They require no evaluation engine to actually run, and you can pull any of these things out and understand it without any additional context. That's the power of data, is that it's really easy to manipulate, and you don't need context to understand what it does. Now, what about computations? How do you compose those? Well, let's say you have a function that returns, takes the message out of a tweet, the string. And then you have a second function that takes a string and just figures out what are the tags inside of the string. So obviously you can compose these things into a bigger system. You can say, get a tweet, and then get the message, and then parse the tags, right? So this would be a new kind of computation. So functional programmers have a tendency to convert this into this kind of syntax, which says, give me a new function that does one thing and then queries it into the next thing. And obviously you can combine this even further. Now you can say, now I have a map, which is some kind of computation that takes a collection and then applies that function, whatever it is, to every single element in the list, right? This is not hard stuff. Like, some people call this higher order functions, but functional programmers just call them functions. It's just the way you program. But notice that each of these expressions, they were always composing computations. So by definition, they were always computations. So the thing about computations is as long as you stick with computations and data, you're always going to get a computation back, which is important because it means that all those properties we talked about still apply. I can take a very complicated system, and as long as you tell me that it's a computation, it has no action in it, I can replace it with what would have been the result of that, and the system works just the same. I can also not care how many times it gets called, right? It can be called once or many times, which is why people keep talking about how functional programming is going to destroy the world with distributed systems. Is because you don't care how many threads are calling the same thing. It doesn't make any change in the system. So those are computations, and then the last thing you have is you have the actions. So you have, in this case, a send tweet, which every time it gets called, it does something. So you need to be very careful about when and how many times you call it. But then, just like any other kind of function, you can compose things together, right? So you can now build a system that every time I send out a tweet, the first thing it does is it automatically likes it, because why wouldn't you like your own tweets, right? So now we have some kind of better understanding of what we can do. Now we have some data, we have some computation, we have some actions, and we have a way of composing them together. What happens when you start mixing it, right? What happens when you take data and you introduce a computation? I can no longer take this expression and move it somewhere else. It doesn't make sense because it's dependent on some kind of context, it's dependent on a computation. So the thing is that computations poison data. As soon as you introduce a computation, this entire expression becomes context specific, right? That's the harm. And you need to do this diligently because basically you took something that had a lot of interesting properties and you ruined it. Similarly, you have a computation. It could be as complex as you want. You don't care. It could be called 0, 1, or many times. And it's referentially transparent. And what do? You make a small change. Instead of taking a collection of tweets, you now do an action. You fetch the tweets from the server every time. And what happens? This entire thing that was a computation now became an action. And now you always have to wonder when and how many times am I calling this big thing and what is it doing? And honestly, I don't know what it's doing because actions by definition, they do things, right? We don't know what they do. All we can do is we can try to figure out how and when and how many times we call them. You know, it's like a Heisenberg uncertain principle. The problem is that even if you call an action and it seems it didn't do anything, did it not do anything or did I not figure out what it did, right? So in the case of, for example, Haskell, you would have monads to basically easier define that this part is an action and these parts aren't. For example, in Clojure, you don't have this characteristic. It's by convention. But the ideas are identical, right? And it's not even functional programming. This same idea applies to all languages. You need to figure out what are your data bits, what are your computation bits, and what are your actions, and split them up. Because if you don't, you have a big problem. As long as you stick with data, you can always compose it and you can get data back. But computations poison that. As soon as you introduce a computation anywhere, you always have to know about the context of everything. And it's even worse if you introduce an action. As soon as something touches an action, the entire thing becomes an action because you can't reason about it individually. You can only reason about it as an entire whole thing that's complicated and cumbersome. And it's really hard to come up with properties about things that you have no idea what they're doing. So, this is what I like to call the 3, stages of programming enlightenment. The first is you figure out how to make it work, right? It doesn't matter if you're doing this in a functional language or another kind of language. You have some amount of information you need to do to figure out how to build systems. If you're doing this in Haskell, then you spend a lot more time trying to figure out how to get the thing to compile, unlike Ruby, right? But at the end of the day, your entire process is to get from 0 to hero, right? You have a non-working system, and you figure out enough to make it work. Now you are a hero. But we don't want to be heroes, we want to be gods, right? So don't stop here. Go forward. The way forward is what a lot of the functional programming blogs and everyone is going to be telling you is identify side effects or avoid side effects. It has nothing to do with avoiding side effects. It has everything to do with identifying them. Identify the actions in your system and figure out ways to make them black boxes that are dependent on as little code as possible and push those things to the edges of the system, right? This has been called many things. This has been called hexagonal architecture. This has been called CQRS. This has been called lots of things. But at the end of the day, you basically just want to figure out where your actions are. You want to isolate them. You want to push them to the edges of the system because those things are black boxes. All you can know about those things is that you can try to figure out when and how many times you call it. And everything else, that becomes your pure code, right? And so a lot of people think that this is what functional programming is, but it isn't. This is just step 2. It's step 3 that really takes it to the next level, you know? This is something FP to 11. Because the next step, after you have isolated your actions in your system, is to not say everything else is pure. That doesn't mean anything. You need to figure out how to reify your code into data. Because if you can do that, then you get a lot of nice properties that fall out. So what does it mean to reify? It's a term I borrowed from the Clojure community because we're really crazy about it. It means to take something that's abstract and make concrete. In the case of programming, in the case of building these kinds of systems, reification means that you want to figure out how to convert a function into a data structure, essentially. Because data structures are things that are easier to manage. and manipulate. So let's look at some examples. So we could call this part 1 of the talk, the theory, and now we're just going to look at a bunch of examples of how to apply this in practice. So routing. Everyone knows how routing libraries work, right? Like essentially what they do. At the end of the day, it's just a bunch of if statements, or a switch, or a case, or whatever you want. It's just basically saying, given some request or some object, go line by line and see if the left side matches. If it matches, then do the right thing. Nothing on the right side, right? So it's a dispatch mechanism. So the easiest way to do this is essentially to write a bunch of ifs or case or switch statements. The problem with this is that it's not maintainable. First of all, it's linear. If the thing you're requesting is all the way at the end, it needs to go through all of the requests, right? So then there's a question of like, how do I order it, in which direction? The second thing is you can't introspect it. There's nothing I can say about this code except look at the source code. I can't ask the router, what kind of routes do you support? Or better yet, can I figure, if I know I want the ping, can you tell me what URL I should dispatch to get the ping? You can't, because if statements, there is no introspection here, right? It's just code that all you can do is you can evaluate it. But it turns out that it's really easy to reify it. So reify is that thing on top. It says, take code and make it data. And we made it into data. We made it, in this case, into a vector of tuples, but we could have just easily used vectors of maps or anything else. It doesn't matter as long as it's just data. The data describes what the computation would have been. In this case, it's tuples of URLs to actions. And then you just write some code that instead of running your system, manipulates the data structures and gets you the answer you want. So you build something like that I called a router, and then that router object is able to analyze and manipulate the code both ways. It's able to match by path, but it's also able to match by name, right? Because all it does is it introspects on the data itself. And secondly, since that thing on top is just data, we can always merge it with more data. We can easily write a second part of our system that has administrative routes, has a separate set of data structures, in this case a dashboard. And notice that roles admin, that's just data. That's just metadata about what the path is. It doesn't do anything. It's data that I supply to the router, and some middleware down the line is going to look at that and go, oh, here's a roles admin thing. I should probably do something about that. The interpretation of the data is completely separate from the description of what it is you're trying to achieve, right? And notice what happens with the router. The router is now just a concatenation of two vectors, right? This is things that every programming language can do. It's just manipulation of data. Next thing that usually comes around is middleware, right? You can't really have a decent routing library without middleware. What is middleware? Middleware is basically, there's a lot of repeatable code that happens when you're handling a request. So let's just move that out and give it a name, and then don't have to repeat ourselves all over the place. So it could be things like logging the total time it took from request to response. It could be things like handling uncaught exceptions and rendering a nice error page. It could be things like serializing, deserializing JSON, validating parameters, checking authorization, right? Things that you just have to do with all requests. But how do you, and notice, by the way, that the way you pass it in is it's just a data structure of, here are some functions that you should chain together into a middleware stack for us. But what is a middleware? A middleware is a function that takes a function, which is the next middleware, as it were, and returns a function that says, if you give me a request, I might manipulate the request in some way on enter. Then I'm going to pass it on to the next middleware in the stack. And then when you're returning with the response, I might have some code that wants to manipulate the response before I push it back up the stack, right? So you've built a middleware. What does that look like in practice? In practice, it looks like this. It looks kind of silly, but essentially what's happening is your request is coming in, and then it goes through 1, 2, 3 middlewares, and each middleware may or may not manipulate the request in some way. It hits the app handler, which is the actual business logic, and then on the way back out in reverse order, the middlewares may manipulate the response before it ends up on the server and on the wire. So again, middlewares are really nice. They simplify a lot of code, but the natural question you should always ask is, can I reify this? And what would that mean, and what kind of properties would that give us? And the answer is interceptors. Interceptors are a reification of a middleware stack because a middleware stack, as you can see, is just a call stack, like a function call stack on your CPU, right? And we can reify it and we can say, no, let's create a data structure that represents the call stack itself, right? So now interceptors, unlike middlewares, are data structures that map certain names to functions. So we say on enter call this function, on leave call this function. And by the way, maybe we want an unerror handler, which basically says instead of doing try catch everywhere, we just have a completely different path that interceptors can hook into if they want to handle errors. And notice that this looks similar to the middlewares, but the functions don't take a request, they take a context. The context is that thing on the bottom. It includes the request still. It may include the response on the way back out, but it also includes a queue, which is all the pending interceptors that have not yet been called, and a stack, which is all the interceptors that have been called that we need to, in reverse order, on the way back out, evaluate if they have an on leave function. So essentially what you've done is you've created a data structure that represents what it means to call functions in your language. And because you've done this, you can now manipulate it, like you can manipulate any data structure. So an example of this in reedit, which is the routing library these examples were borrowed from, you can do things like dynamic routing. You can have interceptors that figure out that I need to push additional interceptors onto the call stack, right? Or I can remove things that would have been called on leave, but I figured out that I don't want those things to be called. You can do this dynamically. So you can create completely dynamic routers instead of having a middleware stack of all the possible middlewares because you're not sure which ones need to be evaluated on a specific request. Additionally, because you are no longer limited to the normal function call stack of call a function, do code, return and jump, and the return and jump means that there's only one place where you can return a value. Since you're no longer limited to this, you're actually creating your own executor. You can create custom semantics. So one of the things reedit does is it says, if you give me a value, I'll just use it as a regular call stack. But if you give me like some kind of promise or something, I can block for you. If you give me a channel, I know that you want to stream data, and I'll pass those streaming channel data up the stack without actually leaving the function. So what that means is it's really easy to implement things like streaming, which are usually very hard to do when you have a regular routing library with middlewares that are based on your programming language call stack. Because functions, by definition, once they return, they're gone. They're popped off the stack, right? Notice from an API perspective, nothing really changes except the name, right? If this looks like or smells like we're writing compilers, it's kind of true, right? We're basically figuring out what are the data structures of our applications, and we're trying to figure out if we reify things into data structures, we can manipulate it and we can create custom semantics of what it means to evaluate it. So by definition, we are sort of creating compilers, and this has nice, interesting properties. For example, reedit does this awesome thing, where it takes the data structure representation of your routes, and it will analyze it. It will figure out if it can build a tree, or a mixed router, or a lookup, or a quarantine, or single static path, or worst case scenario, a linear router. So it chooses the optimal strategy for dispatch based on the routes you give it, right? Worst case, it'll do linear, which means check one by one. But most of the time, it can optimize things. It can figure out ways to optimize your code better than you could do it if you hand-rolled it. And the thing is, it does this automatically and dynamically based on the routes you give it, which has interesting consequences from a performance perspective because, well, as you know, I don't usually give benchmarks because micro benchmarks are useless and macro benchmarks are just fat lies, right? But here, this is a screenshot from this, a set of benchmarks for all routing libraries. And you see reedit up on top. This is limited to JVM-based routing libraries. So this is like Clojure versus Scala and Kotlin. And even though it's nice that the Clojure is up on top, that's not really why I'm showing this. Because like there's Aleph and Aleph really much lower for the Clojure one, right? That's not why this is interesting. What's really interesting is that 97.1%, all the way up on the top right. This re-edit implementation with dynamic routing is only 3% slower than the fastest C++ implementation that was given for, and this benchmark basically benchmarks all known routing libraries. So think about that. We're 3% slower than a hand-rolled C++ implementation in a dynamic language without static typing that gives you the power to do dynamic routing per request, right? This is the power of thinking about how to reify data and then build systems that manipulate and create new strategies for how to evaluate that data. And since we're talking about evaluation, let's move further than just your function call stack. Why don't we just reify what it means to compute things in the large, right? Here's a different example from the Clojure community. It's called Onyx. It's a way of talking about nodes of computation. So this is instead of Hadoop or Spark and so forth. Here you define a data structure that represents the nodes in your system and the edges between the nodes. So the edges are descriptions of how data flows through your system. So in this case, it's really simple. It's just some in node, and then it goes to a split sentence goes to count words, and count words goes to out. In this case, nothing really interesting is happening, and it's a linear process, but there's no reason why you can't do multiplexing, which is basically saying create more edges where a single data node actually outputs to multiple nodes. And there's no reason why you can't do a merge reduce kind of map reduce kind of concept, because a reduce basically means that there's multiple nodes that are all streaming to a single node, right? And this is just data. This is just vectors of keywords that say this is what the graph should look like. And then there's a separate piece of data that says this is what the nodes mean. So in is some Kafka input stream. Split sentence and count words are just functions, and out is some core async channel, right? And I've allotted some details about like which Kafka topic you're pulling from and things like that, because that's not interesting. The interesting thing is this is all data. You can serialize this into a very primitive form and send it across the wire. And similarly to workflow and catalog, you can, in a similar way, describe life cycles, windows, and triggers. And what happens is this entire thing builds this huge JSON file, basically. Only it's Eden, but you can consider it a JSON file. Serializes over the wire, and then you can submit a job. And what Onyx does is it basically sets up a cluster of the amount of machines and the amount of nodes that you said you wanted, and it creates this entire workflow and just runs it for you, right? And you can do streaming or batching using the exact same semantics. It's just a configuration switch, essentially. So that's computations. What about data? Can we reify the data itself? So that's what Clojure spec tried to do, right? It said, what happens if we wrote specifications, data specifications about the data itself? It would be things, and this is based on the semantics of regular expressions and predicates. So here you have things like a tweet ID as a positive integer. We'll create something called a not empty string specification. It's a string that's not empty. A tweet message is a not empty string with less than equal to 140 characters. Tags are a collection of not empty strings. And a tweet, what is a tweet? Well, it's a map with a required ID and message and optional tags. And then over here, the last thing, it's an explanation of what it would look like if you specify functions themselves, their arguments, their return value, and the relationship between the arguments and return. This is not code that runs. This is just data about data. It's just specification. What you do with it is up to you, right? Things that you could do with it are things like you can ask it to describe itself. What is this specification exactly? You can generate some data and you can ask, does this data match this specification? And if it is invalid, can you explain why it is invalid? And because I mentioned, I didn't show on the slides, but this is actually implementation of regular expressions. Regular expressions have branching, right? They have or, and, alts, and things like that. So conform will actually figure out and explain to you, using a data structure, which branch it took on each route. And unform does the exact opposite. So you can conform into a bunch of branches, manipulate the data, and then unform back into a new expression that you can then do something else with it. And this last thing, as gen, it takes a specification and it returns a generator. A generator is something that is used, for example, by test check to generate random data for property testing. But in fact, this is a very generic thing that just says, if you give me a specification, I will give you a generator, and then you can just call next. And I will generate random bits of data that look and match the specification you've asked for. This is actually a cautionary tale as well, because when spec was released, the data about data, these things, sand, scall-of, skeys, they're macros, right? And if anyone has worked with lists before, they know that the problem with macros is macros do not compose. If you take a macro and you want to create a new macro that uses that macro as part of it, you need to create a macro. You can't create a function that uses macros because macros are compile time. So the problem with macros is that they do not compose well. So this created some burdens on developers when they wanted to start creating dynamic specifications. So they dynamically wanted to create data about data as data, and they couldn't. But thankfully, this is Lisp, so the community came out and just built libraries around it. And they reified the Clojure spec itself with libraries like spec tools. And what this proved is you can never have too many levels of data, right? Spec tools is a reification of what it means to create data about data as data that you can manipulate, and then you can ask the system to basically do everything it would have normally done with it. And also, thankfully, alpha version 2 that's coming out from Clojure Core is supposed to also fix this problem. Queries. We've already talked about a lot of kinds of data. This is data log, and I don't have time to talk about data log but it's a wonderful technology. So I gave a talk, and I suggest you just go watch it. The one thing I wanted to mention about data log is notice the syntax. It's a data structure. Data structures are wonderful things to have in your system because they're easy to manipulate, they're easy to introspect, and they represent themselves, so you can serialize them, you can do anything you want with them. Do you know of a query language that isn't a data structure? Anybody used SQL before? If SQL was not a string query language, we would not have 30 years of ORMs, query generators, and SQL injection, security issues. This all comes out of the fact that we're constantly working in a state of manipulating data structures, but for some reason, they decided that the query language is going to be string-based. And so we have to take a bunch of data structures, which we know how to handle well, convert it into a string, which we're terrible at, and 30 years of SQL injections have shown us that we don't know how to do it well. And then the first thing that the database has to do is reverse that process. Take the string and using some weird parser, parse it back into a data structure. Why didn't we just send the data structure over the wire, right? And it's not just SQL. I mean, we can pick on a lot of databases. As far as I know, Neo4j, as awesome as it is, the Cypher, I think that's only string-based. Maybe someone can correct me if there's a data structure version of it. You know what else is string-based? GraphQL. Why in 2019 are we creating query languages that are string-based when the abstractions that we use on a daily basis are data structures? Strings have no right of being in a query language. So that's my rant. That's a data structure. And they figured out, so Datalog is something that runs on Datomic and the JVM, DataScript on JavaScript with DataScript, and then they figured out that, you know what, we can extend this even further. Let's put more data in. So this is something called a pool API. It's an extension of what you saw previously. And what this says is, given a tweet that we found in some way, which is not important for this talk, that thing up on top where it says pool, it says, I've got some reference to a node in the graph, and I want to pull a bunch of information out of that specific node. I can do it by hand in the data log, but I'd like a more convenient way. And so they invented a more convenient way, and that pool query is a specification of what it is I want to pull out of that data graph node. And as you can expect by now, it just looks like more data. This is a data specification for how to do graph and tree traversals. If it's a vector, it's just attributes and the node. If it's a map, it means do a join. So essentially it says, starting at a specific tweet, pull out the ID and the message. Then join it with the user. From the user, pull out the name and the avatar. And then do a reverse join. That underscore is a reverse join. It means, assuming I'm already at the user node, I want you now to find all tweets that point to this user. So find all the tweets this user ever created, and for all those tweets, pull out their ID, timestamp, and tags. Right? And now that we have this data structure, and we've ported it to the back end, and we've ported it to the front-end database, we can port it to all various kinds of other places. So the first thing we did in the Clojure community is we said, why don't, since we're talking, using it on the back end, using it on the front end, we don't need GraphQL. Let's just use it as the API between the back end and the front end. So this is something called EQL. It's an extension of what you've seen up to now. This is no different than what we've seen up to now. Basically, that little hash feed and the hash sidebar are just conventions for, these are not important nodes, they're just placeholders for UI reasons. And we're pulling out a bunch of recent tweets, and then we're pulling out a bunch of attributes from it, and similar for the trending topics. And so EQL took this idea that we started with a database and figured out that we can use the exact same semantics and the same notation to figure out how to do API calls between backends and frontends. And EQL also figured out that we can use the exact same syntax for doing CQRS. This is a notation that says, do a mutation, the new tweet. In order to create a new tweet, I need a user ID and a tweet message. And then because it's a join, it's saying, do a read after the write. And the read says, once you've created the tweet and it was a success, I want you to pull out its ID, timestamp, and URL. Right? Notice that we've created systems on the back and front end between all various weird places using the exact same semantics, right? And because we just used the data structures that were already built into the language, we didn't need to create custom parsers and try to figure out what it means for things to be things. That's a spoiler. I also have a EQL talk. You should go watch it. There's lots of interesting stuff there. This is the last part of the queries. It turns out that since we can do backend, we can do front end, and we can do API between it, why don't we use it in the front end itself, right? So this is borrowed from Fulcro, which is a React wrapper, and that render thing, that's just, so this entire tweet is a React component class. So you create an instance of this, you're basically creating an instance of a React component. So the render is what you would normally render in React. The thing we added, we as in not me, the Clojure community added, was that ident and query part. And the query part basically says, when you want to render, I need these specific attributes in order to render this information. And notice there's those joins we've seen everywhere up to now. And then ident says that if you have like a Redux style architecture where you're storing all your data in a single place, the instance of this tweet ID is related to this tweet React component. So essentially, if the tweet message for this ID ever changes in the database, you need to run render for this specific instance. Otherwise, you don't even need to run this code, right? So it's an optimization on top of what React normally does, because React optimizes the virtual DOM versus the real DOM. And this basically says that we don't even need to create a virtual DOM if attributes that I was dependent on for my render haven't changed in my database. And because this query is just static data, there is no evaluation of code here. It can be interpreted. It can be interpreted in multiple ways. First of all, if I'm creating an instance of this tweet, I need to figure out if I have the data. So I can pull it. I can send that query to my local database on the front end and ask, do you have this data? If so, give it to me so I can render. Otherwise, the system can figure out that it doesn't have the data or it doesn't have parts of the data. So just like GraphQL, it can do a request to the backend, using the exact same syntax notation, and ask the backend, listen, for this tweet ID, I need these specific attributes. And then because this is static data and you don't actually need to run JavaScript to interpret it, the reverse works just as well. If you send the first request to the backend to say, render my application, usually what happens is you send a blank index HTML, which then spins up the entire mechanism for doing React, which then figures out what data needs to be rendered, which then does an API call, which returns the result, which finally renders the application. But here we have static interpretation of data. So in fact, what the backend could do, it could look at this and it could say, I know you're going to need these specific attributes for these tweets. I can send this data along with you. I can either render a version of the static HTML so you can hook it up, right? Or before, when that wasn't available in React, I could just say, I'm going to send you some JSON payload along with your JavaScript. So you can render the first version of your application without doing the round-robin request for actually fetching the first version of your data. And because this is just keywords, remember that Clojure spec stuff? One of the cool things we do is we can generate custom random UI components. So the best way to test CSS is basically to say, create 100 versions of tweet, right? Without any more information, because it knows that a message is a random string. It knows that a random string that's less than or equal 140 characters. It knows an ID is a positive integer. It knows all these things. So it can just generate 100 versions of the data and then run render on it. And it's a wonderful tool, for example, for testing CSS. It just says, there's like a refresh button that says, just show me what 100 tweets would look like, and I'll find the CSS bugs faster than any kind of unit testing would, right? Because I'll do it visually. So we've covered a ton of stuff here, but let's take a step back and remember why we were here in the first place. There's only two things you need to take out of this presentation. This is data. And it turns out there's not a lot of it. There's not a lot of interesting semantic data that you need to know about, but it turns out that it's enough to build all the systems we've been talking about. From front end to back end to distributed clusters. That's all you need. And the other thing is, reach that level of programming enlightenment where data, computations, and actions are separated. Because you don't even need functional programming for this, right? This is something you can apply in any system you build. Figure out what things are actions and try to figure out ways to isolate them so you can monitor when and how you call it. And figure out what things you can convert into data structures, right? You don't need Clojure for this. You can do this with JSON. You can do this with your Java maps, or you can do it with whatever you want. Just create data structures and try to figure out ways of reifying what would have been computation and code into a version with data and then manipulation of that data. And as usual, I'm over time, so I don't think I have time for questions. But you can find me outside, you can find me online, or you can find me at the after party. Thank you.